Something just burned hotter than the sun's own core. For the first time in history, it produced more energy than it consumed. The problem? No material on Earth can contain it, so we stopped trying. This is how nuclear fusion actually works. Every star you can see runs on the same process. Hydrogen atoms, moving fast enough, collide and fuse together. The combined particle weighs slightly less than the two that went in. That missing mass becomes energy. Einstein's equation, E equals mc squared. The sun converts 600 million tons of hydrogen every single second. That reaction has been burning for 4.5 billion years. The problem is that hydrogen nuclei carry a positive charge, and positive repels positive. To force two nuclei close enough to fuse, you have to overcome that repulsion completely. The sun does it with gravity. Its core is 9 times denser than gold, compressed to 15 million degrees. On Earth, we have no gravity like that, so we compensate with temperature, 100 million degrees, hotter than the sun's own core. No material on Earth survives above roughly 3,000 degrees. Titanium melts at 1,600. Tungsten, the hardest metal we have, melts at 3,400. We need 100 million. So a physical container is impossible. The solution is to never touch the plasma at all. When charged plasma moves through a magnetic field, it follows the field lines. Bend those lines into a closed loop, and the plasma follows. Suspended in nothing, touching nothing, held by pure magnetic force. That device is called a tokamak, a Soviet invention from the 1950s, a donut-shaped chamber wrapped in superconducting magnets, holding plasma in a perfect ring. The largest one ever built is ITER, under construction in southern France. 35 countries contributed. The cost exceeds $20 billion. But ITER's goal is not to generate electricity. Its goal is to prove that fusion can produce 10 times more energy than it consumes. For 60 years, every fusion experiment failed at the most basic test. More energy went in than came out. Teams from the Soviet Union, the United States, Japan, and Europe spent decades building bigger and bigger machines. And every time, they fell short. Then in December 2022, the National Ignition Facility in California fired 192 lasers at a frozen hydrogen pellet the size of a peppercorn. About 2 megajoules of laser energy went in. More than 3 megajoules of fusion energy came out. For the first time in history, output exceeded input. The catch: charging those lasers required 300 megajoules from the power grid. Real-world efficiency was under 1%. But the physics worked. The threshold was crossed. That same year, Commonwealth Fusion Systems, a spin-off from MIT, demonstrated the world's strongest superconducting magnet, 20 Tesla, stronger than what ITER is using, in a coil 4 times smaller. The key was a new type of superconducting material that allows far stronger magnetic fields in a far smaller space. That changes the equation entirely. Their compact reactor, called Spark, is designed to produce more energy than it consumes. Helion Energy signed a power purchase agreement with Microsoft, targeting fusion electricity by 2028, and TAE Technologies is pursuing a different approach, using proton and boron fusion, with no radioactive waste at all. The fuel is not scarce. Deuterium comes from seawater. There is enough dissolved in Earth's oceans to power human civilization for 10,000 years. 1 kilogram of fusion fuel releases the same energy as 10 million kilograms of coal. No carbon emissions, no meltdown risk. If the magnetic field fails, the plasma cools in under a second and the reaction stops on its own. For 60 years, fusion was always 30 years away. The magnets now work. The ignition threshold has been crossed. The question is no longer whether fusion works. It is who gets there first and whether the planet can wait. Will fusion be real in your lifetime?